Welcome students, let's discuss chapter 3 Atoms and Molecules. Ancient Indian and Greek philosophers have always wondered about the unknown and unseen form of matter. The idea of divisibility of matter was considered long back in India, around 500 BC. An Indian philosopher Maharshi Kannad postulated that if we go on dividing matter, we shall get a smaller and smaller particles. Ultimately, a stage will come when we shall come across the smallest particle beyond which further division will not be possible. He named these particles Parmanu. Another Indian philosopher, Pakuda Katyayama, elaborated this doctrine and said that these particles normally exist in a combined form, which gives us various forms of matter. Around the same era, ancient Greek philosophers Democritus and Leucippus suggested that if we go on dividing matter, a stage will come when particles obtained cannot be divided further. Democritus called these indivisible particles atom, meaning indivisible. All this was based on philosophical consideration and not much experimental work to validate these ideas could be done till the 18th century. By the end of the 18th century, scientists recognized the difference between elements and compounds and naturally became interested in finding out how and why elements combine and what happens when they combine. Anthony L. Lavoisier set the foundation of chemical sciences by establishing two important laws of chemical combination. 3.1 Law of Chemical Combination. The following two laws of chemical combination were established after much experimentation by Lavoisier and Joseph L. Proust. Now 3.1.1 Law of Conservation of Mass. Is there a change in mass? 3.1.1 Law of Conservation of Mass. Is there a change in mass when a chemical change or chemical reaction takes place? Let's discuss activity 3.1. Take one of the following sets, X and Y of chemicals. Let X be the copper sulfate, Y be the sodium carbonate. X be the barium chloride, Y be the sodium sulfate. X be the lead nitrate and Y be the sodium chloride. Prepare separately a 5% solution of any one pair of substances listed under X and Y, each in 10 ml in water. Take a little amount of solution of Y in a conical flask and some solution of X in an ignition tube. Hang the ignition tube in the flask carefully. See that the solution do not get mixed. Put a cork on the flask. Check out the figure. Pause the video and see the figure 3.1. Now weigh the flask with the contents carefully. Now tilt thus and swirl the flask so that the solution X and Y get mixed. Weigh again. What happens in the reaction flask? Do you think that a chemical reaction has takes place? Why should we put a cork in the mouth of the flask? Does the mass of the flask and its contents change? Law of conservation of mass states that mass can neither be created nor be destroyed in a chemical reaction. Now 3.1.2 Law of Constant Proportion. Lavoisier along with other scientists noticed that many compounds were composed of two or more elements and each such compound had the same elements in the same proportion irrespective of where the compounds came from and who prepared it. In a compound such as water, the ratio of mass of hydrogen to the mass of oxygen is always 1/8, whatever the source of water. Thus, If 9 gram of water is decomposed, 1 gram of hydrogen and 8 gram of oxygen are always obtained. Similarly, in ammonia, nitrogen and hydrogen are always present in the ratio of 14/3 by mass, whatever the method of the source from which it is obtained. This led to the law of constant proportion, which is also known as the law of definite proportion. This law was stated by Proust as in a chemical substance, the elements are always present in definite proportion by mass. The next problem faced by scientists was to give appropriate explanation of these laws. British chemist John Dalton provided the basic theory about nature of matter. Dalton picked up the idea of divisibility of matter, which was till then just a philosophy. He took the name of atom as given by the Greek and said that the smallest particle of the matter are atoms. This history was based on the law of chemical combination. Dalton's atomic theory provided an explanation for the law of conservation of mass and the law of definite proportion. Let's learn about John Dalton. John Dalton was born in a poor weaver's family in 1766 in England. He began his career as a teacher at the age of 12. 7 years later, he became a school principal. In 1793, Dalton left for Manchester to teach mathematics, physics and chemistry in the college. He spent most of his life there teaching and researching. In 1808, he presented his atomic theory, which was a turning point in the study of matter. According to Dalton's atomic theory, all matter, whether an element, a compound, or a mixture, is composed of a small particles called atom. The postulates of this theory may be stated as the follow. First, all matter is made up of very tiny particles called atom, which participate in chemical reactions. Second, atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. Third, atoms of a given element are identical in mass and chemical properties. Fourth, atoms of different elements have different masses and chemical properties. Fifth, atoms combine in the ratio of small whole number to form compounds. Sixth, the relative number and kinds of atoms are constant in a given compound. You will study in the next chapter that all atoms are made up of still matter particles. Pause the video and check the questions. Try to answer these questions. Now we'll discuss 3.2. What is an atom? Have you ever observed a mason building walls? From these walls a room and then a collection of rooms to form a building. What is the building block of huge building? What about the building blocks of an ant hill? It is a small grain of sand. Similarly, the building blocks of all matters are atoms. How big are atoms? Atoms are very small. They are smaller than anything that we can imagine or compare with. More than millions of atoms, when stacked, would make a layer barely as thick as this sheet of paper. Atomic radius is measured in nanometers. 1 by 10 to the power 9 meter equals to 1 nanometer. 1 meter is equals to 10 to the power 9 nanometers. These are the relative sizes. Radius in meter. 10 to the power minus 10. It's the size of atom of hydrogen. 10 to the power minus 9. Molecule of water. 10 to the power minus 8. Example, molecule of hemoglobin. 10 to the power minus 4. It's size of a grain of sand. 10 to the power minus 3. Size of an ant. 10 to the power minus 1. It's the size of an apple. We might think that if atoms are so insignificant in size, why would we care about them? This is because our entire world is made up of atoms. We may not be able to see them, but they are here and constantly affecting whatever we do. Through modern techniques, we can now produce magnified images of surface of elements showing atoms. Pause the video, observe the figure. This is an image of surface of silicon. Point 3.2.1. What are the modern day symbols of atoms of different elements? Dalton was the first scientist to use the symbols for elements in a very specific sense. When he used a symbol for an element, he also meant a definite quantity of that element, that is, one atom of that element. Berzelius suggested that the symbols of elements be made from one or two letters of the name of the element. Pause the video, observe the symbols. In the beginning, the names of elements were derived from the name of the place where they were found for the first time. For example, the name copper was taken from Cyprus. Some names were taken from specific colors. For example, gold was taken from English word meaning yellow. Nowadays, IUPAC, International Union of Pure and Applied Chemistry, is an international scientific organization which approves name of elements, symbols, and units. Many of these symbols are the first one or two letters of the element's name in English. The first letter of a symbol is always written as a capital letter, uppercase, and the second letter as a small letter, which is lowercase. For example, in case of hydrogen, capital H. In case of aluminium, capital A, small l, and not the capital A and capital L. In case of cobalt, capital C and small o, and not the capital C and capital O. Symbols of some elements are formed from the first letter of the name and a letter appearing later in the name. Examples are first chlorine, which is Cl, zinc, which is Zn, etc. Other symbols have been taken from the names of elements in Latin, German, or Greek. For example, the symbol of iron is Fe from its Latin name ferrum. Sodium is a Na from natrium. Potassium is K from kalium. Therefore, each element has a name and a unique chemical symbol. Pause the video and observe the table for more idea. The above table is given for you to refer to whenever you study above elements. Do not bother to memorize all in one go. With the passage of time, a repeated use, you will automatically be able to reproduce the symbol. Let us now discuss 3.2.2 atomic mass. The most remarkable concept that Dalton's atomic theory proposed was that of atomic mass. According to him, each element had a characteristic atomic mass. The theory could explain the law of constant proportion so well that scientists were prompted to measure the atomic mass of an atom. Since determining the mass of an individual atom was a relatively difficult task, relative atomic masses were determined using the law of chemical combination and compounds formed. Let us take the example of a compound, carbon monoxide, formed by carbon and oxygen. It was observed experimentally that 3 grams of carbon combines with 4 grams of oxygen to form CO, which is carbon monoxide. In other words, carbon combines with 4 by 3 times its mass of oxygen. Suppose we define the atomic mass unit earlier, which is abbreviated as AMU, but according to the latest IUPAC recommendations, it is now written as U, which is known as unified mass, as equal to the mass of one carbon atom. Then we would assign carbon an atomic mass of 1 U and oxygen an atomic mass of 1.33 unit. However, it is more convenient to have these number as whole number or as near to whole numbers as possible. While searching for a various atomic mass unit, scientists initially looked 1/16th of the mass of an atom of naturally occurring oxygen as the unit. This was considered relevant due to two reasons. Oxygen reacted with a large number of elements and formed compounds. This atomic mass unit gave masses of most of the elements as whole number. However, in 1961, for a universally accepted atomic mass unit, carbon-12 isotope was chosen as a standard reference for measuring atomic masses. One atomic mass unit is a mass unit equal to exactly 1/12 the mass of one atom of carbon-12. The relative atomic mass of all elements have been found with respect to an atom of carbon-12. Imagine a fruit seller selling fruits without any standard weight with him. He takes a watermelon and says, "This has a mass equal to 12 units." That means 12 watermelon units or 12 fruit mass units. He makes 12 equal pieces of the watermelon and finds the mass of each fruit he is selling, relatively to the mass of one piece of watermelon. Now he sells his fruit by relative fruit mass unit. Look at the figure for better understanding. Similarly, the relative atomic mass of the atom of an element is defined as the average mass of an atom as compared to 1/12 the mass of one carbon-12 atom. Observe the table 3.2 atomic masses of few elements. How do atoms exist? Atoms of most elements are not able to exist independently. Atoms form molecules and ions. These molecules of ions aggregate in large number to form the matter that we can see, feel, or touch. Pause the video. Try to answer these questions. What is a molecule? A molecule is in general a group of two or more atoms that are chemically bonded together, that is, tightly held together by attractive forces. A molecule can be determined as the smallest particle of an element or a compound that is capable of an independent existence and shows all the properties of that substance. Atoms of the same element or of different elements can join together to form molecules. Let us discuss molecules of elements. The molecules of an element are constituted by the same type of atom. Molecules of many elements such as argon, helium, etc. are made up of only one atom of that element. But this is not the case with most of the non-metals. For example, a molecule of oxygen consists of two atoms of oxygen, and hence it is known as a diatomic molecules. So we read O2. If three atoms of oxygen unite into molecule instead of usual two, we get ozone, which is O3. The number of atoms constituting a molecule is known as its atomicity. Metals and some other elements such as carbon do not have a simple structure but consist of a very large and indefinite number of atoms bonded together. Let us look at the atomicity of some non-metals. Here is the table. You can pause and read it. Atomicity of some elements. I can read it out. Like for non-metals, argon's atomicity is it's a monoatomic. Helium, it's also a monoatomic. For oxygen, it's a diatomic. Likewise, for phosphorus, it's a tetraatomic, and for sulfur, it's polyatomic. Let us now discuss 3.3.2 molecules of compound. Atoms of different elements join together in definite proportion to form molecules of compound. Few examples are given in table 3.4. Like compound which is water H2O. The combining elements are hydrogen and oxygen, and the ratio is 1:8. For ammonia, it consists of the combining elements are nitrogen and hydrogen, and the ratio is 14:3. For carbon dioxide, the elements are carbon and oxygen. They are attached in a ratio of 3:8. Let us discuss activity 3.2. Refer to the table 3.4 for the ratio by mass of atoms present in molecules and table 3.2 for atomic masses of elements. Find the ratio by number of the atoms of elements in the molecules of compound given in a table 3.4. The ratio by number of atoms for a water molecules can be found as the follows. Observe the table for better understanding. Now let's move on to 3.3.3. What is an ion? Compounds composed of metal and non-metals contain charged species. The charged species are known as ions. Ions may consist of a single charge atom or a group of atoms that have a net charge on them. An ion can be negatively or positively charged. A negatively charged ion is called anion, and the positively charged ion is called cation. Take for example sodium chloride, NaCl. Its constituent particles are positively charged. Sodium ions, which is Na+, and negatively charged chloride ions, which is Cl-. A group of atoms carrying a charge is known as polyatomic ion. We shall learn more about formation of ions in chapter 4. Observe the table 3.5, some ionic compounds. Let's discuss 3.4, writing chemical formulae. The chemical formulae of a compound is a symbolic representation of its composition. The chemical formulae of different compounds can be written easily. For this exercise, we need to learn the symbols and combining capacity of elements. The combining power or capacity. Capacity of an element is known as valency. Valency can be used to find out how the atoms of an element will combine with the atoms of another element to form a chemical compound. The valency of an atom of an element can be thought as hands or arms of that atom. Human beings have 2 arms and an octopus has 8. If one octopus has to catch hold of a few people in such a manner that all the 8 arms of the octopus and both arms of all the humans are locked, how many humans do you think the octopus can hold? Represent the octopus with O and humans with H. Can you write a formula with this combination? Do you get OH4 as formula? The subscript 4 indicates the number of humans held by the octopus. The valencies of some common ions are given in table 3.6. We will learn more about valency in the next chapter. Observe the table 3.6, pause the video, read the names and symbols of some ions. Now, the rules that you have to follow while writing a chemical formula are as follows. So let's discuss the rule one by one. The valencies of charges on the ion must balance. When a compound consists of a metal and a non-metal, the name or symbol of metal is written first. For example, calcium oxide, CaO, sodium chloride, NaCl, iron sulfide, FeS, copper oxide, CuO, etc., where oxygen, chlorine, sulfur are non-metals and are written on the right, whereas calcium, sodium, iron and copper are metals and are written on the left. The compounds formed with polyatomic ions, the number of ions present in the compound is indicated by enclosing the formulae of ions in a bracket and writing the number of ions outside the bracket. For example, magnesium hydroxide, MgOH2, in case the number of polyatomic ion is 1, the bracket is not required. For example, NaOH, which is sodium hydroxide. Now, 3.4.1, Formulae of simple compounds. The simplest compounds, which are made up of two different elements, are called binary compounds. Valencies of some ions are given in table 3.6. You can use these to write formulae for compounds. While writing the chemical formulae for compounds, we write the constituent elements and their valencies as shown below. Then we must cross the valencies of combining atoms. So let's understand these examples. First, formula of hydrogen chloride. Write hydrogen and chlorine separately and write their valencies below them. So you can see hydrogen has one valency, chlorine has one valency. So the formula becomes simple HCl. Now let's consider second, formula of hydrogen sulfide. Here you can write the valency of hydrogen, which is 1, and valency of sulfur is 2. So that means the sulfur has valency 2. That means sulfur must combine with 2 hydrogens, and hydrogen has 1 valency, so hydrogen must combine with 1 sulfur. So the formula becomes H2S. Let us move to another formula, the third, carbon tetrachloride. As you can see, the carbon has 4 valency. That means carbon must combine with 4 atoms. So here you can see chlorine has 1 valency. That is the reason here carbon, the formula becomes CCl4. It means carbon is attached to 4 chlorine molecules. Just because carbon has 4 valency means it has 4 valency, it can bond with 4 chlorines. That is why CCl4 becomes the formula. Similarly, for magnesium chloride, magnesium has 2 valency and chlorine has 1 valency. The formula becomes MgCl2. Now, thus in magnesium chloride there are 2 chloride ions. For each magnesium ions Mg2+. The positive and negative charges must balance each other and the overall structure must be neutral. Note that the formula, the charges on the ions are not indicated. Here are more examples. Pause the video and understand the formula. Here the valencies of two elements are same. You may arrive at the formula Ca2O2, but we simplify the formula as CaO as it got neutralized, +2 and -2. Here are more examples. Pause the video and understand the formula. Let's discuss the formula of calcium hydroxide. Note that formula of calcium hydroxide CaOH2 and not CaOH2. It means the OH must be in the bracket. We use brackets when we have 2 or more of the same ions in the formula. Here the bracket around OH with a subscript 2 indicates that there are 2 OH molecules. It's not separately 2 oxygen molecules and 2 hydrogen molecules. This is not the case. Here it says 2 hydroxyl. It means OH. They are in bonded form. There are 2 types of there are 2 groups of hydroxyl. That is why it is enclosed in a bracket. There are 2 atoms of each oxygen and hydrogen in calcium hydroxide. Now let's discuss 3.5 molecular mass. In section 3.2.2 we discuss the concept of atomic mass. This concept can be extended to calculate molecular masses. The molecular mass of substance is the sum of atomic masses of all the atoms in a molecule of substance. It is therefore the relative mass of a molecule expressed in atomic mass unit, which is U. Discuss the example 3.1. Calculate the relative molecular mass of water H2O, and the second question is calculate the molecular mass of HNO3. So look at the solution. First we have to calculate the relative molecular mass of H2O. First find out the atomic mass of hydrogen, which is 1 unit. Oxygen is 16 U. So the molecular mass of water, which contains 2 atoms of hydrogen and 1 atom of oxygen, is 2 multiplied by 1 plus 1 multiplied by 6, which goes 18 U. Now the second answer. The molecular mass of HNO3 equals to the atomic mass of hydrogen plus the atomic mass of nitrogen and multiplied by 3, there is 3 oxygen. So the atomic mass of O multiplied it by 3, which equals to 1 plus 14 plus 48 gives 63 U. Now let's discuss 3.5.1 formula unit mass. The formula unit mass of a substance is a sum of atomic masses of all atoms in a formula unit of compound. Formula unit mass is calculated in the same manner as we calculate the molecular mass. The only difference is that we use the word formula unit for those substances whose constituent particles are ions. For example, sodium chloride has discussed above has a formula unit NaCl. Its formula unit mass can be calculated as 1 multiplied by 23 plus 1 multiplied by 35.5, which is equals to 58.5 U. Let us discuss an example 3.2. Calculate the formula unit mass of CaCl2. So first, atomic mass of Ca plus 2 multiplied by atomic mass of Cl, because there is a 2 atoms of Cl, so it is multiplied by 2. 40 plus 2 multiplied by 35.5, which is the mass of Cl, so it gives 111 U, the mass of calcium chloride. Now pause the video and check out the question. Try to answer it. So let's discuss what we have learned. During a chemical reaction, the sum of masses of the reactant and product remain unchanged. This is known as law of conservation of mass. In a pure chemical compound, elements are always present in a definite proportion by mass. This is known as the law of definite proportion. An atom is the smallest particle of the element that cannot usually exist independently and retain all its chemical properties. A molecule is the smallest particle of an element or a compound capable of independent existence under ordinary conditions. It shows all the properties of substance. A chemical formula of compound shows its constituent element and the number of atoms of each combining element. Cluster of atoms that act as an ion are called polyatomic ions. They carry a fixed charge on them. The chemical formula of a molecular compound is determined by the valency of each element. In ionic compounds, the charge on each ion is used to determine the chemical formula of the compound. So, these are the exercises. Pause the video and try to solve them. Thanks for watching.